I'm going to present a bit of an overview today of what we've done in 14.3 and mainly what we've been doing for 15.0 that's coming out soon. All right, so let's start with the most important thing first. So this is the most important slide, and it shows you where to find examples. So these are links, and if you click on them, you'll get to the help system. And that will guide you to the PDE models overview page. So that page has a collection of PDE models from different fields like acoustics, electromagnetics, fluid dynamics, heat transfer, mass transport, quite a few by now. And those sections are always structured in the same way. So the first one is like a mass transport, PDEs and boundary conditions, a guide page that lists all the functions that we have in this specific domain. It lists a monograph that's associated with these functions. It has a list of application models in that area. And what's also quite useful is it has an overview of what different application models provide. So for example, if you're looking for a transient, a time-dependent system, these two are the application examples you might want to look at. All right, so, and then, so if you go to the mass transport, then there is this monograph that I've just mentioned. It has a, can quickly look at that. So there's a section on different aspects of mass transport modeling, an introduction, some equations, and some explanation of what's been modeled in this specific area. Then we usually have a collection of models, the mass transport models, also already mentioned on the guide page. It shows some examples. And the last section that you'll find is a mass transport examples. So these link to typical examples in reference pages, like the NDSolve reference pages and things like that. So that's another source of information. Right. So if you're working in a specific field that's not been listed on this PDE models overview page, that doesn't mean that we cannot solve that specific PDE. It just means that we don't have this elaborate set of monographs and functionality for that, but not all hope is lost. You can still solve quite a few more PDEs than we've listed in this overview page, just to make you aware of that. All right, so but now let's have a look at what has been added for version 14.3 and the upcoming version 15. So we have some news in the basic building blocks in the PDE terms. There's some updates for heat transfer, solid mechanics, electromagnetics, and fluid dynamics. And then there's some things that are not quite related to PDE modeling, but more the underlying infrastructure. There's some new functionality for linear solve and extrapolation method. I'd say the theme for the 15.0 release is provide more what you typically in the finite element world would call post-processing functions. That's not the only thing we've done, but you'll see that there are a few new functions to get results from the originally obtained result to post-process them and get more functionality from them. One thing I'd like to point out specifically is there is a new application example that's called, it's an introduction to PDE modeling. And if we go back to this page, to the PDE models overview page, it's listed right up here, the boiling of an egg. And this is a very good first application example. If you're new to PDE modeling, it starts from a very basic egg boiling simulation and goes quite fancy. So, and that's done step by step. And typically what we do in the application examples, we just present the final application example. But this one here explains a bit how we set these models up and how we ourselves develop these models from a very simple basic starting block, basically flesh it out to something really complicated. Okay, so that's something, and Ricardo is giving a talk about that tomorrow. So if you're interested in that, that's something I'd like to recommend you to look at. Right, PDE terms. So the addition for PDE terms are coordinate charts. So that means if we look at an example, so for example, I have the diffusion term, the dependent variable, the independent variables, the coefficient is 1. I can now add the coordinate chart goes, for example, to polar, and you can use any coordinate chart you like. It's going to return a new PD term. If we activate that, we can compare this, for example, to the Laplacian polar coordinate, and we see these are exactly the same results. We've added this. This will become a bit more apparent a little bit later why we've added these coordinate charts, but I think that's a useful feature to mention in any case. So if you want to do PDE modeling in other coordinate systems, you can now much more easily do that. In heat transfer, there was a small update. We've added a thickness parameter that makes it a bit easier to model in 2D cases. So when you have a heat flux going through a surface, you no longer need to adjust for that. The thickness parameter will adjust that specific value to the exact thickness of the object that you have. I don't have an example for that, but it's something worthwhile mentioning, and there's some documentation about that. All right, so let's look at some more stuff. So in solid mechanics, I'm very pleased to announce that we've made a good step forward in plasticity. And we'll get to that in a second. There is a new post-processing function, equivalent strain. We have new boundary conditions, a spring and a damper boundary condition, and the boundary force and pressure can now also be expressed as a normal force and a normal pressure. This last item is useful when you have curved boundaries. So you used to have to specify each component of the boundary normal, but now you can just specify a single value for the force or the pressure, and the code will take care of adjusting it to the normal of the boundary. So that's a good thing. Right, so plasticity, there is going to be a new monograph that talks about plasticity, what it is, how to use it, gives examples and things like that. There is going to be another talk tomorrow. Alessandro is going to give the talk, and he's going to exclusively talk about plasticity. So if you are interested in plasticity, I'll recommend you go to that talk as well and have a look at what Alessandro will show you there. I'm just going to give you like a few highlights of what we can do now. So plasticity is a permanent deformation of an object if you bend an object, for example, beyond its yield limit. So if you use the standard elastic model, you'll continue endlessly to increase the stress on the object, but that's not the case for plastic deformations. At some point, when you hit the yield limit, the code now needs to go in a completely different branch and compute the incremental of the strain doesn't result in an increment of stress. So that's basically what yielding does, the yield limit does. So here's an example of a soil that is under pressure. So here we'll have some load on this soil part with the slope, and now you can see the green lines represent the failure lines. So that's how the soil would slide. But again, Alessandro is going to talk a bit more about that, these details tomorrow. One last thing I want to mention about plasticity, we can also model load hysteresis. So basically, when you start to put pressure on the deformed object, you increase the load, it yields, it continues to slowly increment, and then at some point you unload the object. The unloading takes a completely, or can take a completely different path than the loading, and we can also replicate these type of behaviors. Yeah, so I recommend you, I'll send you to Alessandro's talk for more details about that. The new function equivalent strain is basically a von Mises stress for strain. So the von Mises stress takes the stress tensor and converts it into a single interpolating function, and the same thing happens with the equivalent strain. So it takes the strain tensor and converts it to an equivalent strain. So the equivalent strain and the von Mises stress are basically companion functions and compatible companion functions. They behave in the same way. So here's an example. I have a beam with some holes inside. I set up the dependent variables u, v, and w. X, y, z is the independent variables. I have a titanium chosen as material. and the displacement is computed with ND-solve values, solid mechanics PD component to set up the equations, Mars parse. And now we have a boundary load value at the right-hand side here. We have a force of -2 to the 10 to the 7th in the negative z direction, so it's downward forcing. And we have a solid fixed condition on the left-hand side, so that's where it's held fixed. And that's the displacement computation and the strain computation exactly the same like in previous versions. There's nothing has changed, but now the strain is a symmetric 3x3 tensor, and the equivalent strain is reducing that 3x3 tensor to a single interpolating function, and you can then visualize that in the deformed object. So that's a new function. Okay, so what are these spring and damper conditions? So sometimes a Dirichlet condition is too forceful. That means you can say with a Dirichlet condition that an object is deformed by a certain amount, but you may not necessarily want that. So imagine that you're pressing down on soil. So the soil will give in to a certain degree, and this can be modeled as a spring. So what we have here, so as an example, is a rectangle, some material parameters. We have a plane strain case here. We set up the PDE component fixed condition. So that means on the left-hand side, this beam is held fixed, and we have a solid boundary load value. So we have a pressure again in the negative y direction. So that's applied somewhere here in the middle, and that's the deformation of that object. Now, what we can do in version 15 is we can add another solid boundary load value. That's now, this is on the right-hand side, so it's acting here. And we can specify a spring constant. So in this case, I've specified 10 kilonewtons per millimeters. It's going to be converted to SI base units. And now we see that we have something that's pressing up here. So that's a new type of boundary condition. This is a spring boundary condition, but we can also do the same thing as a damper. And a damper is usually used when you have a time-dependent system. So they use exactly the same code. Spring is for the stationary case, or it's a spring constant, and damper is only relevant when you have a time-dependent system. Okay, so electromagnetics. Here we have two new post-processing functions as a magnetic flux density and magnetic field intensity. They compute the B and H field respectively, and they work for both scalar and vector potentials. Here's a small example. So to compute the magnetic flux density, there's a mesh. Inside that mesh is a region that is a magnet, and outside is air. And we want to compute, so the magnet is transversely magnetized in the direction of the y-axis. That's what's happening here. The magnetization is given. And then we can compute the interpolating function from this, the magnetic potential. But now you want to compute the flux density, and you use the magnetic flux density Mars parse and specify the magnetic potential, and it's going to excuse me, it's going to return the interpolating functions that you can then plot. So these are typical or classical post-processing functions. You have an interpolation function that you get from ND-solve. It's a direct result of your simulation, but you want to do something else with it because you're not interested in the vector potential, but you want the flux density, for example, and that's something we can do now easier. So this function will take care of multiplying the material constants and whatnot. If you have a magnetization, it takes care of that. So all of these things are done inside these functions. Previously, you had to use something like gradient and multiply it with the material constants to do this. But this is now all packaged up in these functions. That's yeah. Right, for fluid flow, we have also new post-processing functions, fluid viscosity and fluid viscous stress. Martin is going to talk about this. It's a little bit later today. And he's also added verification tests for our fluid flow capabilities. So there you can have a look at some classical textbook examples for fluid flow, and we show that we can solve them properly. We've also added swirl flow, and I'm going to show an example about that now. So if you consider axisymmetric flow means that the theta variable, the rotational variable, is set to 0, and by consequence, the derivative of that theta is also set to 0. Swill flow has a little bit of a less stringent condition. There, you only specify that the derivative of the rotational component is set to 0. So you can have a rotational component, so theta can have a value, but the derivative is set to 0. So here's an example. This is a mixer, a 3-bladed mixer that's in a beaker. It's axisymmetric, so but we want to compute the rotational, or we want to see the rotational effect this mixer has on the liquid that's inside when it's rotated. So I've generated a mesh here, and then I specify the variables. So U, V, and W. So note that this is a 2D example, but still I specify the third component, the V component. So that's the theta component here. I specified dynamic viscosity, mass density, and here now again is the coordinate chart that we've seen earlier. So now I can say the coordinate chart, this will then, the fluid flow PD component will now dispatch to the low-level PD terms, and they understand correctly what to do with the cylindrical coordinate thing. So this will now generate the correct equations. I need some boundary conditions. So here now I set that the rotational velocity is r times omega, and omega is a parameter. I'm going to use parametric ND-solve in a second, so we can change this parameter. This gives the rotational speed of the mixer's rod. Some other boundary conditions, we have a wall boundary condition, the symmetry axis. At the top, we have a condition, and we have a reference pressure. So this is all standard fluid flow things. Yeah, so now I create the parametric ND-solve value of the activated operator. The boundary conditions are specified, U, V, W, and P are given. The mesh is given, and omega is the parameter, and I specify an interpolation order. So this is our way to say that we want to use a specific finite element. In finite element terms, it's a Taylor-Hood element. That's the way to specify this. But what's interesting now is, so now I can say the function that I've generated, if I have an angular velocity of pi, I'm gonna get these functions now that I can look at. So I use function interpolation, the square root of all velocity components squared, added up, over the mesh. That's going to give me a new interpolating function, which is a velocity magnitude. So function interpolation was introduced in 14.3, and we can now visualize the results. So this is when the rotating mixer is in the fluid. This is the velocity magnitude of the fluid. We can also do this in a manipulate. That's because I've done this with a parametric version. So now you see, as we increase the speed of the mixer, how the fluid magnitude changes over the increased speeds. Okay. Right, so linear solve. So now we're switching gears a little bit. So now we're going more into the linear algebra and lower level finite element things. There is a new method for linear solve that's called MUMS. So MUMS is a specific solver. We specify a sparse array, a right-hand side linear solve, sparse array, right-hand side, method goes to MUMS, and it will happily solve this equation. Why did we add this? So we have the problem that Mac ARM hardware cannot use the default finite element linear solve method, which is Paradiso, because it's shipped with Intel and it's working only on Intel hardware. So in version 15, MUMS is going to be the solver, the default finite element solver on ARM hardware. In version 14.3, we had to use, so this comes up often in highly nonlinear problems, that the default solver we had for ARM would fail. But in 14.3, you could give this specific option, linear solve MUMS, to get to a solution. Or an alternative in 14.3 was to use Rosetta, and then you could use the standard commands. But in version 15, we've made this fully automatic now. So in version 15, you can call this piece of code, and it will detect that you have an ARM, Mac ARM hardware or any ARM hardware, and we will use the MUMS solver automatically for ARM hardware. Yeah, that's just one thing to be aware of. Another thing is we're thinking about, or we're working on adding an option to interpolation, which is called extrapolation method. And what it does, it's so if we have this interpolating function, 1, 2, 3, blah, 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 we get this interpolating function, and we evaluate that interpolating function outside of its domain. So 0 is not part of this domain. It's going to give a message and says that 0 is outside, and we will use extrapolation to compute something. So it's computing -1 as a function result. If you specify now this extrapolation method goes to indeterminate, we get a new interpolating function. We get, again, a message that the value is outside of the range, but extrapolation is used, and now we get the result indeterminate. And this can be any function you like. You can add, like, you could make this to 0 or whatever you seem fit. You can also switch off the message if you don't want to see a message at all. So this gives you a bit of more control of what interpolation does when it has to extrapolate the data. Okay, right. Then we've added new application examples. So this is now back in the PDE modeling domain. There are two new physics-related examples. So there is a Schrödinger-Poisson type of example that iterates between a Schrödinger equation and an electrostatic equation to find a specific potential. So that's one thing. Then we've added a Schrödinger-Newton equation example. The system modeler team has provided an interface or a new application model where we couple system modeler with finite element computation. The next two, the spine surgery rod and the slope stability, are both plastic deformation examples. So this is a rod that's used in the spine to stabilize the spine, and it has to be deformed so that it fits the spine perfectly. And slope stability is something from civil engineering, so where you have to estimate the stability of a soil slope, whether it's going to hold or not, or what to do about that. Then we have two new examples in bio. One is in biomechanics, so it's a human tendon. So if you are hurting your tendon, you can estimate how it's going to behave. So that's one example. And the last one is a 3D print of, have a look at that one, 3D print of a mechanical design. So what we've done here is we've created various designs for a hook. So these are an initial version of that. And then we've used, so we create different hooks. Let me scroll down a bit to show you the, oops. Oh, no, I skipped too fast. So there are the three different hooks. And now we can use finite element analysis to assess which one of these hook designs is suitable for the application that we have in mind. There is an additional kind of complication is, so when you 3D print, you want some parts of it to be hollow so that you don't use too much material. So that can also be taken into account. So with different design patterns for that, use that. And then, I mean, you compute this and you can compute the von Mises stress on the different designs and have a look at what seems suitable. And you can make an assessment of which one of these functions or which one of these forms is the winner for a specific load scenario that you have. Right, okay. So I think, yeah, so that's the last slide. So thank you for attending. One thing I would like to raise some awareness for is that we try to have a yearly PDE finite element conference. These conferences are specifically for PDE modeling and finite element related things. If you're here at this talk, you might also be interested in this conference. Unfortunately, I don't have a date for you yet when the one for next year is going to come, but stay tuned. Be aware that we do have these conferences, so maybe that's something you'd like to keep an eye on. All right, so let me quickly go to see if I have questions. Okay, so first question. Given that normal forces and pressure can be applied, do you plan to also enable the direct application of tangential forces and pressures? Good question. Yeah, maybe that's actually a good. I haven't done that yet, but maybe that's actually a good suggestion to also have not normal pressure, but also like a tangential pressure, tangential force. That's actually a nice idea. I didn't think about that, but that's certainly something that could be thought about. Yeah. Okay, so for modeling the factor of safety for soil slopes, the normal approach is to perform shear strength reduction analysis. In essence, reduce the soil shear strength parameters, typically cohesion and single angle of friction, until failure occurs. Yes, we have a shear reduction example in the application. So in the slope application, you will find that shear reduction analysis that's going to be done. Yep. So next question is, any suggestion on how to become familiar with functions and tools for mesh creation? When I see the code in examples, it makes sense, but it would be good to develop an intuitive understanding for new problems. What can I recommend for that? So I think, so this is, I mean, probably different people would give you a different answer for this, probably also for depending on which team you'd ask. So in 2D, I think you're pretty well set with the standard functions that are built in the Wolfram language, with maybe the exception when you generate multi-material regions. For those, I'd suggest to use two-element mesh. And there is a, I mean, maybe it can be, let me go back here. So if your mesh generation, maybe that's a good thing as element mesh creation. Let's see what that. So there's a tutorial element mesh generation that has a lot of material on the finite element mesh generation. Now that's not the entire story. That's just for the finite element mesh. You can also use mesh region and the top level or system built-in functions for this. So that's options, and you'd have to play a bit around and see which one suits you best. Start with the mesh region stuff first, and when you hit problems, then go to the element mesh generation, because they are really suited for finite element generation. One last thing, recommendation I can give, Open Cascade, let's see. For 3D generation of geometries, complicated geometries, I typically say try to use the Open Cascade link, because that's quite powerful. You have standard conversions, but what's more interesting is probably the operations on these objects. So you can do sweeps, Boolean operations, shape splitting, shape sewing, like internal boundary generation, fillets, chamfers, lofting, shelling. All these things can be done with the Open Cascade object. So if you have something more complicated, then I'd probably say Open Cascade is the way to go for that. I hope that that answers the question a bit. Yeah. Okay. Let me see if there's another question. Yeah. So another question. I was wondering what's going on behind the scenes that improves the performance of a PDE component compared to its explicit analog. Okay, so I assume a few things now. So I assume the question is that you have an example where the PDE is solved more efficiently when you use a PDE component compared to when you type it out in a specific way manually. The reason I could imagine that you're hitting or seeing is that the PDE's terms that we generate with the PDE coefficients fit very well with the PDE parser that we have. So they're optimized for that. And the PDE parser can make efficient code out of that. So I assume that is the reason why it's more efficient to use the PDE terms. It shouldn't be a whole lot of a difference, but I can imagine cases where this actually is can become a difference. Okay, so I think I've answered all the questions. So I'm gonna hold here. Thank you.